Hey kids, here we are for the beginning of Unit 4, where we are going to learn how to apply everything that we did in the previous units, all the way from limits to derivatives, right? How definition of derivative to all our derivative rules, right? All of that is leading us to now, how do we use this stuff, right? So this whole chapter, this whole unit is all going to be no new rules, right? How do I use the derivatives? The first application that we're going to do is the mean value theorem. AP loves to call this the MVT. Okay. And since it is a theorem is proven, right? And it has an if and a then. And what AP really, really cares about is if you know the conditions. Sure, I need you to state the mean value theorem, but I'm never going to, on an assessment, neither is AP going to say, write out the mean value theorem. What they're going to do is ask you to use it, and they're going to ask you to verify that you are allowed to use it, which means you have to know the conditions under which the mean value theorem applies. So let's state it first. There we go. The mean value theorem. Notice the if, so certainly put this in your notes and highlight the if part and the then part. If you have a function, how long have you been dealing with functions? If that function is continuous, how long have you been dealing with continuity? They restrict you to looking at this continuous function over a closed interval, right? So that includes endpoints. And then there's something new. What's the new part? Must also, those conditions have to be met, and you need to also be differentiable. There's your calculus piece. To be differentiable, remember what that means? Smooth, obviously continuous, we already said. No corners, no breaks, no cusps, no vertical tangents. On the open interval, right? So they don't care about, right? If you have the differentiable part doesn't matter for the end part, the endpoint, right? I just have to be differentiable on the inside. Doesn't matter whether I'm differentiable or not at the end. Then, if you satisfy all four of those conditions, function, continuous, have a closed interval, and on the open interval, you are smooth, no corners, no breaks, no cusp, no vertical tangent. Then there is some point C, which is a domain value. And that domain value, right, we usually think of that as an X, right? The theorem uses C. If you call it an X, no one's going to care. But it is between A and B. This C value is going to be between A and B. And remember, A and B come from your closed interval. If all of that is true, then there is this statement. I'll think about what this statement says. Hello, Algebra 1. What this is, calculus is equal to Algebra 1, because this is just your change in Y or change in X. This is the slope of the secant, or the average rate of change. If the conditions of the MVT are met, there is slope of the tangent. That's what the derivative is, right? Slope of the tangent, which is an instantaneous rate of change. They are equal at some place, as long as you satisfy the mean value theorem. So I'm going to draw a very simple, I would have a better or a more detailed picture, but let me draw something really simple. Here's a parabola, upside down parabola. Pretend it goes through the origin there. And it hits the x-axis there. So the x-intercepts. There's my A and there's my B. What's the slope of the secant connecting A and B? The slope of the secant is 0. I hope that's obvious. Can you see a place on the parabola where the slope of the tangent is also 0? In other words, where is the secant parallel to the tangent? We can see that's right there. Now, did I satisfy? Now, I didn't even think about the mean value theorem. I just drew those. But now, let me think about the mean value theorem. Is this parabola a function? Tis. Is it continuous? Well, it's continuous everywhere, but is it continuous on the closed interval that I chose? Yes, since it's continuous everywhere, it's certainly continuous on on any interval. But can you imagine, like, for instance, if I had a rational function may be broken somewhere, but if I choose an interval where the vertical asymptote doesn't exist, right, is past it or before it, I can still apply the mean value theorem. So I have to be continuous, but I don't have to be continuous everywhere, just on this interval. Am I differentiable on the open interval, A and B? Well, again, a quadratic is differentiable everywhere, so I certainly am differentiable in between A and B. If those things are true, then I was guaranteed to find this tangent where the average rate of change over the interval was the same as the instantaneous rate of change over the interval. And further, look at the point of tangency. The point of tangency is some x comma y, but that x value was between A and B, and the mean value theorem calls that C. So yes, it was an x, and yes, this was a y, but the mean value theorem likes to say this was C, comma, f of C. And further, that the instantaneous rate of change at C is equal to the average rate of change over the interval AB. Here's a nicer picture. Right? At some point in the closed interval, the actual slope, and think instantaneous, equals the average rate of change. So here's a function. It is smooth and nice, continuous, differentiable. There's the slope of the secant between two randomly chosen points. I have a function. The function is continuous on AB. It is certainly smooth and nice and differentiable on the open interval AB. So therefore, can you use the mean value theorem, right? And again, I don't need the mean value theorem to see that I have, right? I just lay my pen here, drag your pencil up, keeping it parallel to the slope of the secant, up to the line until you see a point of tangency. Boom. There is a tangent parallel to the secant. And further, what is true about the point of tangency? The x value, which the mean value theorem calls C, is between A and B. Hey, take a moment and look at what that is. Look at what's on that bridge. Let me go back a minute. Look at the mean value theorem. Conclusion. This is an equal sign. Since there's an equal sign, I can multiply by whatever I want. And what if I multiply this side by B minus A and this side by B minus A? What do I get? The instantaneous rate of change times the change in X is equal to the change in Y. What? I've just rewritten that. That is still the mean value theorem conclusion, isn't it? Think about what it says, though. The instantaneous rate of change is a slope, and a slope is always the change in Y over the change in X. B minus A is the change in X. What happens when you multiply that? You get the change in Y. Oh my goodness, mind blown. Math is cool. So look at my statement in red here. There is a city in Beijing where they consider this so important, they put it on their freaking bridge. What do we put on our bridges? Come on now, right? Look at that. Crazy. All right, let's do a problem. So this is a very traditional mean value theorem problem, one that you'll find in your book, right? Given a function, find the value of C. So what am I trying to find? A domain value. But I need to satisfy the mean value theorem. So if they ask you that, make sure you state that. So what am I going to say? Well, hello, I have a function, right? Function notation. X squared is continuous everywhere, so it is certainly continuous on the closed interval. X squared is a polynomial, so it is certainly differentiable everywhere, which means it is differentiable on the open interval. So those are the conditions. Function, continuous on closed, differentiable on open. Now, of course, that was sounding silly for x squared, right? Because x squared is both continuous and differentiable everywhere. But I don't need a calculator for this, right? I know in my head what x squared looks like, and I can chop it off at the points 0, 0, and 4, 2. I'm sorry, 2, 4. So again, I draw a secant line, and I can visualize this. I can draw a secant line, and then I can drag my pencil down to the function until I see a point of tangency, draw a tangent line, and then what I'm after is the x coordinate. That's what this is asking me for. So since I have satisfied the conditions of the mean value theorem, then I can write this statement. Calculus is equal to algebra 1. No, I don't care if you write that out. You can go directly to this. Right? Change in y over change in x. 4 divided by 2 is 2. Check my visual. Does it look like the slope of these lines equal to 2? I buy it. Now let's take care of the other part, f prime of c. And again, I don't care if you say The only reason they use C instead of X is because they're saying C is a particular value of X, because really X represents the entire domain. I don't care if you use X, but technically f of C is equal to C squared. What is the derivative of, right? I just replaced X with C. The derivative is 2C. So 2C is equal to 2. C must be equal to 1. Check location. Is 1 in between 0 and 2? Yes, it is. Done. That's all they asked me for. So again, very routine, standard problem. Now, this problem, we had a function from a worksheet that was